My name is Naveen Verma from Princeton University, and I'm going to be talking about a technology that has the potential to serve as a platform for creating large numbers of distributed and diverse sensors. This is a technology called Largearea electronics, and I'm going to be illustrating its use through medical sensor applications. So what is Largearea electronics? So this is a technology that we achieve by processing thin films of materials at low temperature, so like at 200 degrees Celsius. So this compares, for example, to silicon CMOS, which is the workhorse technology we use to create all of our microprocessors, which requires processing at well over 1,000 degrees. Now, low temperature is important because it enables compatibility with a wide range of materials, which we can use to create diverse sensors and energy harvesters, which we can use to fabricate these on substrates like glass and plastic, which can be large and flexible. So as an example over here, I've shown just a small sampling of the kinds of sensors that have been achieved and the kinds of form factor that's been achieved. So for example, this is a sheet that integrates pressure sensors with 3mm pitch on a sheet that's flexible and on the order of a square meter. Now let's think about the use of this technology for medical sensor applications. It turns out that this attribute of large area is important because in our body, signals occur on a micron scale, but they can be distributed over the dimensions of us ourselves, which is meters. And in fact, these dimensions can be much bigger when we consider that the way that we interact with our environments has important indicators for diagnosing disease, for monitoring disease progression, and so on. So sensing signals over those dimensions needs a really unique kind of technology. The attribute of thin and flexible is important because the subsystems, biological subsystems in our body are highly functional on a chemical level, on an electrical level, mechanical level, and so on. So we want to be minimally obtrusive to all of these processes and their structure. Now, the attribute of diverse sensing is important because across these different domains, electrical, chemical, mechanical, we have a range of signals that we could be interested in. And so thanks to this alignment, we've actually seen very simple sorts of large area sensing systems emerge. For example, for interfacing to the central nervous system, for interfacing to the skin, where we can measure biopotentials, for interfacing to the peripheral nervous system, and so on. But the problem is that sensors alone do not address real-world applications. For that, we need systems. So we need to combine these sensors with functionality for instrumentation, computation, power management, communication, and so on. Now, it turns out that in large area electronics, we can actually create low-temperature processed thin film transistors. And indeed, people have started to demonstrate various components for these sorts of functionalities using these devices. But let's do a reality check. It turns out that low temperature processing, the same thing that's so good for sensing, leads to transistors that have orders of magnitude lower performance and lower energy efficiency than what we would get out of crystalline silicon transistors. As an example here, I show some numbers for two different TFT technologies, amorphous silicon and a slightly higher performance technology, zinc oxide. You can see here that the mobilities for these devices are 2 or 3 orders of magnitude lower than what we would get for silicon transistors. Now, it turns out that low temperature deposition of the gate dielectric leads to reduced quality, so the gate stack scalability is limited. This leads to thicker gate dielectric, and both of these factors combine to give us much higher supply voltages, which increase the energy. Now, in addition to that, when we process these thin films, they expand and they contract, and so we need larger margins for the overlap regions. That leads to higher capacitances, and as a result, all of these things combine together to give us an FT, a unity current gain frequency for these transistors, which is 4 or 5 orders of magnitude lower than what we get from silicon transistors. So the point is that large area electronics on its own really can't create complete systems, at least not of the sophistication that we'd like. And so this has led to the concept of a hybrid system, which combines large area electronics with higher performance technologies like silicon CMOS. Now, for example, taking from this quote by Carver Mead, one model for building these hybrid systems might be to take all of your sensors and put them in the large area domain, and then basically take all of the other system functionality you need and delegate it to the silicon CMOS domain. And in fact, that would be a reasonable rule of thumb. But it turns out that if you dig a little bit deeper, what really limits these hybrid systems is the interfacing that I now need between these two technology domains. And in fact, it turns out for that, there can be specific thin film functionality that really helps us address these interfaces. So as an example, I've given you a reference here that analyzes some of those functionalities and takes a look at the architectures that we might build around those. But to give you a feel for how we might actually build these systems and what the challenges are, I'm going to talk about a particular system. This is for acquiring electroencephalograms and processing EEG. So EEG, or electroencephalograms, are signals, electrical signals from the brain that we can measure on the surface of the scalp. This system is going to highlight the need for two kinds of thin film functionality. The first is low noise amplifiers. The reason we need this is that in this technology, we like the fact that the sensors are distributed, in this case over the scalp, but the CMOS ICs are centralized. And so this leads to these long interconnects which are susceptible to noise due to stray coupling. So it'd be nice to have these localized amplifiers to mitigate that sensitivity. The second functionality we're going to need is scanning circuits. So the idea here is to reduce the number of interfaces from a large number of EEG channels to as small a number as possible. So in a typical montage, we might have 20 channels, but in fact, in many applications, we can have well over 100 EEG channels. And it's the interfaces to the silicon chip that are going to limit the reliability, the cost, the scalability, and so on of these systems. So we want to reduce these number of interfaces. So let's start by looking at this low noise amplifier. Now it turns out that shot noise sources are fairly fundamental. What I mean is that whether you're a silicon transistor or a thin film transistor, this is basically going to affect you in the same way. On the other hand, 1/f noise, which is actually the dominant noise source in the band of interest for EEG acquisition, is of particular concern for thin film transistors. So this is a source of noise that is originating because of trapping and detrapping of carriers in the semiconductor and the semiconductor dielectric interface. And it turns out that with low temperature processing, we don't have the ability to create a nice crystalline structure. So we have a higher density of these traps. Now we can address this, so as a result of this, the 1/f noise is particularly elevated for these devices. Now we can address this in the usual way by increasing the dimensions, the width and the length of these devices, and indeed this works for these thin film transistors, as I've shown over here with some measurements. But the other challenge that we have is that low temperature deposition gives us this lower quality gate dielectric. So we have this increased probability of pinholes as we increase our dimensions, and that increases the failure rate. So this sizing is really a limited knob for these devices. Now, as an alternative, you can look at circuit techniques. For example, chopper stabilization is an approach where we first up-modulate our signal to a higher frequency band, which is less affected by 1/f noise. Then we amplify it, and then after we're done amplifying, we demodulate it back down to baseband. And indeed, this works well for addressing 1/f noise. But the problem is, we now need to run our amplifier at a higher frequency, and that has a cost on power efficiency. So to be more specific, over here I show the noise power spectral density of a TFT amplifier. And you can see at this particular biasing, the 1/f corner is at about 5 kilohertz. So that's really what I want to modulate my signal to. That means that I need to design my transistors to have an FT that's about an order of magnitude higher than this. And that affects my power efficiency. So one metric for power efficiency is the amount of transconductance that I get for a given bias current. This is called the transconductance efficiency. And it turns out that increasing the FT degrades my transconductance efficiency. The reason is that I need to use, for higher FT, narrower devices in order to reduce the capacitance. But then to get back the transconductance, I need to use a higher bias current, which increases the static power consumption. So for example, here I show the transconductance efficiency for these two TFT technologies, which is degrading at higher FT. In fact, it would be degrading for silicon transistors as well, but the FTs in this regime are so low that these transistors can basically operate in subthreshold, where the transconductance efficiency is relatively constant. But the interesting thing to note is that while many of these TFT parameters are orders of magnitude worse than silicon transistors, actually the transconductance efficiency is not. It's worse by about a factor of 20 at my targeted FT in this application. And in fact, that's for an amorphous silicon TFT. If I look at a zinc oxide TFT, a slightly higher performance material, in fact, this can be much better. So the reason for this is that while these TFTs have lower transconductance, they also have lower current. And so this overall ratio is actually not so severely impacted. And so if this form factor of flexible and distributed amplifiers is important, as it might be in a case of distributed sensing around the scalp, in fact, these amplifiers are quite viable. Now let me come to the scanning circuit. The big challenge here is that the limited performance of the TFTs gives me a speed of this for the circuit of about 10 kilohertz. Now EEG is fairly low bandwidth signal, maybe a couple of hundred hertz. But in fact, the problem is that implementing brick wall filters is not feasible, especially not in the analog domain. So we really need to budget a kilohertz or a couple kilohertz for each of these channels. So with this speed limitation, under Nyquist sampling constraints, we would be severely limited in the number of channels we could support. But it turns out that we can do something better than generic Nyquist sampling by exploiting sparsity. So in fact, EEG, time domain EEG, exhibits sparsity when we take its Gabor transform. And so it should be that with a small number of non-zero coefficients, I should only need to take a related number of samples to really nail down this signal. Now, in fact, it turns out that there's a theory called compressive sensing, which tells me that in order to do this, I don't even need to transform to the Gabor domain. In fact, I can just take random measurements as long as these are incoherent with this Gabor transform so that I capture all of the degrees of freedom in some way. And this will be enough. And so as a result of this, signal acquisition is significantly eased. Now, before I show you the thin film circuit that we use to do this, let me just address that while signal acquisition is made easier, actually reconstruction of my signal is quite difficult under compressive sensing. And the reason is that I actually need to now solve for a sparse solution in the Gabor domain. And the usual way of doing that is something called L1 norm minimization, which is computationally intensive, too much so to perhaps even implement on an embedded low-power IC. So let's, instead of doing reconstruction, think about just extracting features of the EEG. So these are attributes of the signal that I might use for doing some subsequent analysis. It turns out that a generic biomarker of the EEG is the spectral energy distribution. So in particular, the way that I extract the energy of, say, a vector x is by taking an inner product of this vector with itself. So really what I care about is this quantity over here. And this does not require a sparse solution. So I can actually solve for this using a much simpler L2 norm minimization, which has a formulation that I'm showing over here. Turns out that this is a convex minimization, and so it actually has an analytical solution, which leads to a very simple linear transformation. But what's interesting is that this particular linear transformation also has the structure of basically taking random measurements on top of my previous random measurements. Now, what's interesting about that is that when I go to take the inner product, as I've shown over here, these random measurements essentially fall out as an identity matrix. What I mean by that is that gamma transpose gamma approaches an identity matrix because its elements are uncorrelated with each other. And so I can basically extract the energy of this original vector from these compressed estimates. And so taking this approach, where we've done something slightly different, we also want to apply a filter in this case so that I can extract the spectral energy in a particular band of interest. But taking this approach, you can see that we actually achieve very good estimates for these energies. So here I'm showing measured results for various different compression factors, and you can see that these match very well compared to an approach based on Nyquist sampling. So this is the actual prototype. You can see what we've implemented over here is a chopper stabilized amplifier with an input modulator and an output modulator using thin film transistors. The way that we take the random measurements is we actually then modulate that signal by a random ±1 sequence. We then apply a very low frequency cutoff low pass filter, so basically an integrator. Turns out that applying this filter is like doing convolution. That's similar to multiplying a input signal vector by a matrix. And so this amounts to taking those random measurements that I need for, say, a compressive sensing framework. So we've implemented several of these channels on this flexible substrate. These are some measurements acquiring EEG from a human, but let me start with some amplifier results. Over here I show that thanks to chopper stabilization, in this case to a frequency of 5 kilohertz, in fact the noise is reduced as we would expect. The common mode rejection ratio also benefits from chopper stabilization, so you can see here with this chopping, it's above about 40 dB. Now I should say that 40 dB is not really enough for EEG acquisition, and so this turns out is limited by mismatch in these transistors, which we think comes because of its fabrication in an academic fab, but this is really something that we now need to address. Here we're acquiring EEG from a human. This is being done from an electrode in what's called the occipital location. This is a location in the back of the head near the visual cortex. When you close your eyes and you enter a relaxed state, it turns out that what pops up is this 10 hertz rhythm called an alpha wave. And so we're going through periods of closing our eyes and being in a relaxed state and having this alpha wave emerge. And then it going away and then reappearing when we close our eyes again. Over here I'm showing the compressed acquisition of EEG and then sparse reconstruction at various different compression ratios. But in fact, as I mentioned, what we're really interested in doing is extracting the features directly. And so you can see over here that actually doing that in the way that I mentioned, we're able to achieve very significant compression ratios while maintaining the performance of seizure detection, which uses the spectral energy distribution as a feature vector for classifying the onset of a seizure. Okay, so some summary and conclusions. I really wanted to highlight this technology, large area electronics. It gives us something transformational, the ability to create these large numbers of distributed and diverse sensors, but it really doesn't give us a path for building complete systems. And that's why I think we really need to think about hybrid systems that combine large area electronics with, say, silicon CMOS. Now, when you go and do that, it turns out what really limits you are these interfaces. And so to address these interfaces and make these systems viable, we really need to think about specialized circuitry and indeed specialized architectures that will require some unique thin film circuits and components. But in addition to that, we also want to think about algorithms that can help us address these interfaces. For example, the case of this direct feature extraction from the compressed signals. So there's this real sort of system, I think, approach that is going to be required to enable these hybrid systems. Hopefully this was a little bit of an illustration of that.